All right, so welcome again, everyone, to another exciting organic chemistry class. This is a quick review of General Chemistry 2. Let's get started. All right, so first question, what is organic chemistry? All right, so organic chemistry is really the study of carbon-containing molecules, but the focus is really on the movement of electrons. That's really the focus. So here's a typical reaction where you have, this is referred to as a substitution reaction, where you have a hydroxyl group attacking a methyl iodide, and the iodide is substituted by a hydroxyl to give you your alcohol. So in essence, organic chemistry is really focused on the study or the movement of electrons, not necessarily atoms. All right, and then why should I care? Why is this important? For most of you guys, based on what you said, you're interested in heading into the medicinal field, whether as a pharmacist, a doctor, researcher. So in terms of applications, our organic chemistry have applications in the food industry, clothing industry, pharmaceuticals, plastics, and in terms of just a typical reaction, we can convert an inorganic molecule like ammonium cyanide just by heating that to form an organic molecule like urea, as shown. All right, so here are the brief highlights of chapter 1. I'm just touching on the brief highlights. All right, so first thing you want to learn about is what's constitutional isomers. What is that? So constitutional isomers are compounds that have the same molecular formula, but they're connected differently. And when I say connected differently, it means that they have different constitution, right? In terms of the oxygen being connected to a carbon versus a hydrogen, they're just connected differently. That's all it means, all right? So different molecules will have different physical properties, also different chemical properties. So like if you notice on the far left, we have like dimethyl ether. It has a boiling point of -23. Ethanol, that has the same molecular formula, but different connectivity, has a boiling point of 78.4 degrees Celsius. All right, so that's as it relates to the structural theory. Now, another thing that's important that you need to know or you need to remember is this, connectivity, right? Always remember that for carbon, carbon is tetravalent, meaning that carbon is always bonded to 4 different atoms. Nitrogen is trivalent, means it's attached to 3. Oxygen is always divalent, it's attached to 2 other atoms, whereas the halogens, like your fluorine, chlorine, bromine, are monovalent. They're always connected to 1 other atom in order to satisfy its valency. So to have like a full octet, right? Remember that. So that's as it relates to the connectivity of the different atoms. So if you go back to the periodic table, your job is to memorize what groups do the different atoms come in. Like say boron is in group 3, carbon is in group 4, nitrogen is group 5, oxygen is in group 6, fluorine is in group 7, and so forth and so on. Because this is important in calculating like formal charges, which we will do today. So just to remind you of where the elements appear in the periodic table. All right, so next up we have Lewis structure. So Lewis structure just kind of talks about the different atoms and their valence electrons, right? So if you take ammonia as your target molecule, if you kind of break them apart, ammonia, the nitrogen in ammonia has 5 valence electrons, right? So 3 of the electrons are involved in the bonding, whereas 2 electrons are unpaired. We refer to those unpaired electrons as a lone pair, right? So when you draw like a Lewis structure of say ammonia, this is what it would look like, right? And then when you kind of draw that structure, you'll notice that there's a lone pair that's present that's not connected to any other atom. Check. And then another topic that you'll look at is what's referred to as a formal charge. So formal charge means that if the net charge on the molecule is negative, you'll have like a minus sign on it. And that's referred to as an anion. If it has a positive charge, it's referred to as a cation, and that's important. And then also, if we go back to the periodic table, you'll remember the term electronegativity. So the trend is, as you go from left to right, electronegativity increases. That's because we're increasing the number of protons in your atom. And then as we go from bottom to top, electronegativity also increases, all right? And why is that important? That is important as it relates to bonding. So if you remember the different types of bonding that we discussed in general chemistry, you have like your covalent bond, your polar covalent bond, and your ionic bond. So how does electronegativity affect that? So as the difference in electronegativity changes between the two atoms, like say if you move from a carbon-carbon bond to a carbon-oxygen bond to like a nitrogen-chlorine bond, as the difference in electronegativity increases, the bonding changes. So it's no longer a covalent. It goes from covalent to polar covalent to ionic. So it's more like an attraction and a sharing of electrons, right? Then we jump on to atomic orbitals. So if you guys remember in Gen Chem, when you talked about the Aufbau principle, Pauli Exclusion principle, and the Hund's rule, that kind of talks about how electrons are filled in the atomic orbital. So if you remember the Aufbau principle, it says that you start at the lowest energy level, moving all the way to the top energy layer. So the Pauli exclusion principle just tells that electrons in the same shell must have opposite spin. And Hund's rule just pretty much says that once you reach a degenerate orbital, like the p orbital, each electron have to occupy a single orbital before you start to pair them up. That's all that's saying. And what does that mean? In terms of the implication of this, it has to do with another topic that we'll cover that's talking about hybridization. And hybridization is just talking about bonding, right? How do we represent this atomic orbital theory in terms of bonding? So if we talk about a carbon atom being sp3 hybridized, what does that mean? So if you guys remember from general chemistry, hybridization is just a mixing of atomic orbitals where you may have a 2s mixing with a 2p, so you end up with 4 degenerate sp3 orbitals, and that kind of explains the shape of an sp3 orbital. It has 25% s character, 75% p character. So let's say the right side is the p, left side is the s, and in terms of bonding, for carbon, it has 4 sp3 orbital. That's the reason why carbon is tetravalent. So it means carbon always bonds to 4 different atoms. Does that make sense, guys? So that's the reason why carbon is tetravalent, because it's sp3 hybridized, meaning it always bonds to 4 different groups. Yep. Now let's look at the different example. Let's look at an sp2 hybridized carbon. So for an sp2 hybridized carbon, what am I saying with that? So in that particular scenario, you have one of the s orbital, the 2s orbital, that mix with only 2 of the p orbitals. So one of the p orbitals is left unaffected. So what you have as a result of the hybridization is you have 3 sp2 hybridized orbitals. What does that mean? So that simply means that you have a p orbital that has an electron that's unaffected. You have 3 sp2 hybridized orbitals. So the question is, how does that affect bonding? Here's how it affects bonding. If you have two carbon atoms that interact with each other, they form a sigma bond overlap, and then the p orbital that was not affected forms what we call a pi bond, right? So if you remember when we talk about double bond, if you guys remember double bond, it's formed from the overlap of the side overlap of your p orbital and your sigma bond, right? So that's how you get your carbon-carbon double bond. And then how do I get my carbon-carbon triple bond? Same deal. In this scenario, you're just simply reacting an s orbital with one of the p orbital, so you only form two degenerate sp orbitals, and you have two p orbitals that are unaffected. And as a result of that, you have like a sigma bond with another carbon, and then you have two side p orbitals overlap to give you your triple bond. So what's the takeaway from all what I'm saying? The takeaway is this, guys. All right, so a triple bond, in terms of its strength, it's stronger than a double bond, and a double bond is stronger than a single bond. In terms of the length, the triple bond is shorter than the double bond. Why? Because the triple bond has more S character than the double bond. And likewise, the double bond is also shorter than the sp3 hybridized carbons, because it has, for the same reason, it has more S character than the sp3 hybridized carbon. Check. Almost done. So with chapter 1, the next topic that you want to look at is what's called the VSEPR theory. That's a valence shell electron pair repulsion. So that kind of tells us the shapes of the different molecules in terms of, is it trigonal, is it pyramidal, is it bent? So that's pretty much that. That's a topic that's covered in that sense, and that's all based on what's called the steric number. I'm not going to go into details with that. I'm going to let you guys read that. So based on the steric number, if it's 4, like when you do the addition, like say steric number, like how many sigma bonds are present, how many lone pairs are present, if the number is 4, it just means that the shape of that atom will occupy a tetrahedral type geometry. If the steric number is 3, it will be like an sp2 hybridized type geometry. If it's 2, it's sp. What do I mean by that? So here are some examples, right? So in the example of, say, methane, carbon in the middle, 3 hydrogens at the end, the steric number for this is 4. So that means that the atoms, the hydrogen atoms are kind of spread out in a tetrahedral type format. So they're far away from each other as possible, right? So for like methane, it has like a tetrahedral type geometry. For the ammonia, which is a nitrogen that has a lone pair, it also occupies a tetrahedral type geometry. But because you have a lone pair, we can ignore that and say that it's more like a trigonal pyramidal type geometry. And then for water, it has 2 lone pairs. It also occupies a tetrahedral geometry. But with the lone pair, if you remove the lone pair, we'll say that water has a bent type structure. So if you summarize everything, looking at the steric number, if it's sp3 hybridized, it occupies a tetrahedral type geometry. So if there are no lone pairs present, it's tetrahedral. If it's 1 lone pair, like in ammonia, it's trigonal pyramidal. If it's 2 lone pairs, it's bent like water. Boom. So that's one example. If your steric number is 3, where it's an sp2 hybridized orbital, like say like your boron trifluoride, the shape or the arrangement of the atom would be more for trigonal planar. And if it's an sp type geometry, like, you know, like dry ice, carbon with 2 oxygen, it's linear because you have 2 double bonds. So that's a summary of what to expect as it relates to the VSEPR theory. So I'm just giving you guys just a taste of what to expect when you read through chapter 1. It's an easy read. The Kent text is a student-friendly book, so you will not have any problems in reading the Klein text. Is that so far so good, guys? In terms of a quick summary of chapter 1? Any questions regarding
Yes.
so far so good? All right. Okay. And then just to wrap up chapter 1, the only thing that is completed, you guys covered this already in Gen Chem, when you talk about dipole moment and net dipole moment, that has to do with the electronegativity in the molecule. So say, you know, chlorine is more electronegative than carbon, so it has like a net dipole moment in one direction. So that's the reason, you know, the phrase that says like dissolves like. So if your molecule has a strong difference in electronegativity, like your water, it's going to be polar. So only polar substance will dissolve in polar substances, like, right? And then if your molecule is non-polar, like your hydrocarbons, only non-polar molecules will dissolve in non-polar substances. So like dissolves like. That's just a takeaway for that particular topic. And finally, the key thing that you should remember is a review of the type of interactions between intermolecular forces, like your dipole-dipole interaction, your hydrogen bonding, your dispersion forces, which you already know. So an example, if you have a polar molecule that has dipole-dipole attraction, it's going to be more stronger than one that is a non-polar type attraction. How do I know that? They have an increased boiling point, increased melting point. If you compare acetone to like isobutylene. Another example, hydrogen bonding. Molecules with hydrogen bonding have a stronger affinity to each other, so they will have a higher boiling point than molecules that don't have hydrogen bonding. And likewise, in terms of application, in terms of your DNA, you see that the different bases, they are connected by hydrogen bonding, right? In terms of your alpha helix, your beta sheets, right? And one fun thing to remember, if we shift gears to London forces are the weak intermolecular forces called dispersion forces. And a good example of that is your gecko. If you notice, you see like gecko run up and down the walls. That has to do with the fact that they have a lot of tiny hairs on their feet that can help them to kind of connect with the wall through weak dispersion forces. And that's the reason why they can run all over your house and scare you. Next up on dispersion forces is, as you increase the carbon chain length, you increase the surface area. And if you increase the surface area, it just means that you increase the connectivity of the dispersion forces, so that increases the boiling point. However, if you start to branch, as shown to the right, then that decreases the surface area and that decreases your boiling point. So that is your summary crash course of chapter 1.